86 I was in Stanford, and I was at Hewlett-Packard. Okay, I was working at Hewlett-Packard at the lab of Hewlett-Packard. I met Hewlett, just to say. Okay, but we actually, Hewlett came to my. I was working, and Hewlett came to me and said, "What are you doing?" Okay, so I was not polite with Hewlett. Okay, I didn't know it was Hewlett. Okay, so it was young. Anyway, so this is the book. If you have the opportunity to find it, it's a pleasure to read. Okay, and it was in 85. You see, it was in 86. So this is the first book. Was the first book on this topic. So I mean, it was impossible to find in Italy. There was not Amazon at that time. So I needed to go to Stanford bookstore. I remember, okay, there were 2 copies, and I grabbed one, and the other was another guy that grabbed the second one, and it was gone. So the other had to wait 2 weeks. So anyway, and let me show you some examples. Application, some of the applications that you can read here is like adaptive modeling, adaptive system identification, which is what we discussed. Inverse adaptive modeling, the convolution equalization, which is the opposite of what we discussed. Adaptive control is a control. Adaptive interference cancelling. Blah, 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 blah. Let me go there. Let me go. Which page is that? Adaptive interference cancelling is 303. Should be around here. No? Which page is that? 303. Could be here. Let me see. 303. Just to show you on this book, so this is the picture about the signal source, primary. This is the same scheme that we discussed, okay? So we have a reference that is measuring the primary, and then we are measuring the noise source, and we are applying the adaptive filtering such that I cancel the interference. Okay, so that's one, but there are more esoteric, stationary noise cancelling, blah blah blah. Let me see. There is one that was very. Okay, that's another one. Okay, another system where for instance, we have a correlation between, for instance, this is the signal, this is the noise, and unfortunately, the signal is leaking there, and leaking of the signal is degrading the performance of the overall canceller because I'm cancelling the interference cancellation. What was the title of the paper? Adaptive noise canceller. Okay, it was from IEEE. So now, this is from the last year. You see, these are the notes I made last year. So, for instance, if you have a sinusoid, and you will see that the workshop will probably, I give you this exercise, I need to think about it. So, if I have a sinusoid and I have a signal, and the signal is affected by the sinusoid, so there is a sinusoid superimposed. So if I need to cancel that sinusoid, which goes on the top of the signal, now the sinusoid can be 50 Hz noise from the power line, but can be something else, like the homework of the last year. So, one way to cancel the sinusoid is by combining cosine and sine. Because if I combine cosine and sine, then, by changing the coefficient that I use to combine, I can create, an arbitrary amplitude and arbitrary phase. And some of the students last year in the homework, they changed it to create an amplitude, not just a phase, but also a frequency varying sinusoid. So that is one possibility. So, and you can use adaptive filtering. Now, this is the LMS algorithm, so it is mu gradient. Okay, so it's the gradient formula. Huh? And tell me.
Sorry, in this diagram, what's the meaning of this arrow in filter?
Oh, the arrow is because it's varying.
Okay.
We discussed last time. So when you have a box, a filter, and there is a line that goes in this direction, okay, that means that the filter is varying. Now, since there is this line which is connecting there, okay, so that means that the filter is made vary depending on the output. That is the meaning. Okay. Now, specifically, now this one is the unzip for that, if you like. Okay, unzip. So is detail for this compact block diagram. And the detail is that this is the input and this is the output. So I take this signal here, I take the two input, and then I use to change the two coefficient. Okay, so then if you like, you can say that is a block missing, but when I indicate it's adaptive, it's implicit in the word. Some of the students last year, they came to me and they solved the homework remembering this discussion. Okay, so solving the homework is also looking around. Now, another way is that when I cancel the interference, when I cancel the sinusoid, it looks like if I'm applying a notch filter. A notch filter is a filter where you kill the sinusoid. And since you want to remove a sinusoid, that is a notch. Specifically, that filter is an adaptive notch filter. Okay? So that's, I'm just serving a different possible application. Now another one, let me go to the baby, which is always so nice. Okay. This is the picture also from the journal paper. This is the picture where you have the echocardiogram, and you have some 50 hertz, 60 hertz in US, but so you have some interference. And even if you put a twisted pair, the telecom will understand why they put a twisted pair. So even if there is a twisted pair, there is still some power line, okay, which is entering, and you want to cancel that. Okay. Now another. Okay, this is the echocardiogram. This is the echocardiogram with the sinusoid, which is due to the power line. You know what the power line is? The lamp light. Oh, this is the disaster. They create a lot of interference. The neon, that lamps. Okay, so and they create something like that. So you have A is the data, which is affected by this sinusoid. You have the reference sinusoid. You remove this to that by changing the coefficient, and you start with that. The adaptation, you see, adaptation begins, and when you adapt, after a while, you get a clean signal. Okay, this way you remove a sinusoid, and okay, these are some. That's another one. Is also creating a lot of fantasy to people. I mean, when you need to think about this was in 75. Okay, in 75 you were not born, right? And you need to think that it was the early stage about making digital signal processing. Really early stage. Okay, now your cell phone can make a lot of computation, but that time you had something like a digital signal processor was machine like that big. Okay, now it's nothing. Huh? Now it goes into a pacemaker, which goes into the body, and you can recharge it. And at that time, the people were fighting about making the Fourier transform, the discrete Fourier transform, fast. Okay, now you use the fast Fourier transform, right? But at that time, the people fight. There was a competition about describing an algorithm that was making the Fourier transform fast. And the IBM won because they made the Radix 2 Fourier transform, which is the FFT, fast Fourier transform that you guys, we all use it, okay? But they won, and it was a secret, and nobody knew why. And they made the FFT, you know, fast, and everybody was getting crazy. Oh, IBM, how IBM? You know, it was a very active time. You know, I mean, I was in Silicon Valley in '85, '86. You know, I remember that time, and I was in the same lab of Steve Jobs. I was, you know, was coming there. And there was a might of these people that were coming and going. I remember one of the guy that cooperated with him to create Apple. I know he was sitting in three desks far from me, and we chatted. So you know, when you look at back, it's really was very, very interesting time. Okay, my only complaint is that I came back to the recall. So you know, then, but then you know, that's another, okay? And so you have a mother and a child, and you want to make the echocardiogram to the child. Now, the mother is stronger than the child, so the echogram of the child, the poor child is very small, so the heart beating, but you know, the heart is that big, and you know, we have an heart that is that big, so you know, and the noise, the electrical noise that makes, you know, this compared to the other is very big. So now to make the measurement, you need to cancel the beating of the mother. Okay? So you make an active cancelling for the beating of the mother. That's another one. So you know, you start with this, which is affected by the power line. So you have a power line, you have a child, and then after, when you cancel that, you have a mother, you cancel the power line, you start to see the fetus. And after canceling the mother, you get the fetus. And you know, this was in '75, you know, which was magic at that time. Now you measure, you have, now it's currently done. So now you probably, what I want to do is to transmit you why there was a lot of enthusiasm. And by the way, you need to remember that at that time, the people were moving from the electronics into the digital signal processing, because digital signal processing could do the time-varying filter. In electronics was impossible. I mean, even now, it's not so easy. You need to change a capacitor, blah, blah, blah. So, you know, trick a track, you know, it's complicated. In digital signal processing, come on, you change a number and that's it. Okay, so that's why a lot of enthusiasm in those years. And that's why I moved from analog signal processing, which is electronics, into digital signal processing. Okay, so I am a son of those enthusiastic years. Let me say it this way. Now, after that, let's go to the point. Okay, so there are some examples here, I don't know, here, so on, blah, blah. But the methods are still the same. Yeah, here they are making with a telephone, but you know, now it's made for the satellite, the echo cancelling and the satellite. Now they're always on, but you know, I remember when I was in California, and I was calling Italy, and you know, sometimes when you bounce to the satellite, they don't plug in, they don't insert the echo cancelling, so you can listen your echo. It's not nice. It's not nice, because when you talk, it's not nice. Probably some countries, I know, some of you experience the noise, the echo, when you call families, they are far away. So, that's some. So, there are many applications for adaptive filtering, so many that this justify the enthusiasm of the people. Okay? Now, so let's go to the point. So, what we did is to calculate the step size to guarantee the convergence. The convergence of what? The convergence of adaptive filtering. Remember, you know, let me write here. Where can I write here? I had a page. So, iterative, probably is still there, no. Iterative, okay, remember, iterative is R and P are known. Okay? And then the things are known, I can search, I calculate the gradient of J with respect to A, okay, where J, which is the cost function, contains out and cross correlation that are perfectly defined, okay? And from here, so I search that, I implement it, then I find that the mu is smaller than 2 times lambda max. Now, if I don't want without oscillation, I choose mu smaller than 1 over lambda max. And the time for convergence is approximately equal to lambda max over lambda min. Iterative. Adaptive. Adaptive, you know, the error is I use the instantaneous error. Since I use the instantaneous error, I implement not just the gradient, but you know, I replace the gradient with the stochastic gradient. Okay, so I plug in and replace with that. I cannot expect that to have the same condition for convergence. Now, by chance, I found that the convergence in mean, the convergence in mean is that, you know, mu is smaller than 2 to lambda max. Convergence in mean is the same as iterative. Iterative means I know R and I know P. Okay? Now, the convergence in a mean square error means that the mu is smaller than 2 times trace of R. Now, since the trace of R, okay, is the trace of autocorrelation, okay? Now, let's make some thought about on this. So this is what we concluded up to now. Let's make some thought. Now, the thought we can make is that, you know, now mu square error, so I need to have mu smaller than mu square error, which is 2 divided by trace of R. Now, what is the trace of R? Now I go to the property of algebra, and I know that trace of R, okay, is equal to the sum of all the eigenvalues. Okay. So, you know, what's happened that? It happens that, I mean, surely mu square error is smaller than 2 divided by lambda max. Because in one case is the sum of the numbers, in the other case is 1 over just one number. So, you know, it's clearly small. Now, let's, you know, we are engineers, so we need to have a number that we feel. We need to figure out something. I mean, we find, you know, completely confused with this formula. We need to have a very stupid, simple formula to remember. Quick and dirty is always a must for an engineer. Quick and dirty, something to remember. Then, if I need to do more complicated, I can do it. Give me time, give me money, I sit and do. But you know, if you expect a very quick answer from me, and you need to have it, you must have it. So, you know, let's see what is a quick and dirty answer. So, I mean, how much is the time for convergence for convergence in a mean square? What's happened with that? So let's consider the case where, you know, Rxxk, which is the autocorrelation, is equal to sigma square x multiplied by delta k. So what does it mean? It means that, you know, the input is white. Okay? So input is white. Okay? Now, since the input is white, I mean, then all the eigenvalues are the same. So that means that lambda 1 is equal to lambda 2 is equal to lambda n is equal to sigma square x. Now, let's compare the two conditions, the convergence in mean and the convergence in the mean square. Now, convergence in the mean. Convergence in the mean says that mu should be smaller than 2 times over lambda max. But since all the lambda are the same, then this is equal to 2 divided by sigma square x. Okay? Because they are all the same. Right? Convergence in mean square m, or mean square. Mu is smaller than 2 times sum of lambda k, but they are not the same. And so this is equal to 2 divided by n on sigma x squared. In other words, it's 2 divided by sigma square x multiplied by 1 over n. So mu is n times so smaller. Mu is n times smaller. The time of convergence is n times bigger. So the convergence in the mean square is n times slower than the convergence in the mean. But the convergence in the mean does not exist. The convergence in the mean is a pure exercise. Is a pure, is something that is not related to the reality for adaptive filter. So what dominates is the convergence in the mean square. And the convergence in the mean square is n times bigger than the convergence in the mean. But n is the length of the filter. So the time for convergence depends on the length of the filter because it's incremented by m. So making the filter longer means having higher variance because we studied in the past that estimating more coefficient means having higher variance. But estimating more coefficient, which is making m big, means making the adaptive filtering slower because it takes n times more steps to converge. N is number of steps.
What if we change we have some kind of switching? We approach by using the first method, we have bigger mu, we reach to the zero mean, and then we change the phase and start sliding around the zero mean by using
you can, all that are artisan implementation. What I'm saying is that no. I'm saying it depends on the case. I'm not giving the answer to any problem because any problem has its own. So that means you know that you can do that. Okay, then you try. So perhaps you make 4 steps with the bigger mu, then you reduce the mu. Now I'll give you another, but the intuition is fine. Okay. Now I give you another insight to refine this intuition that you have. Okay. I give you, give me 5 minutes, 10 minutes, and I give you an additional 10 minutes I don't have, but I try to make. Okay. Now, last point. That's the additional point. Okay. So I know this is the derivation, blah blah blah. We said that this is not part of the program, and you can check it. So what I found is the following. I found that even if I reach the convergence, the filter's coefficient fluctuates. Okay, you can see from here. The filter coefficient fluctuates. So these fluctuations means that when I ski down, I reach the bottom of the valley, I keep moving. This is the fluctuation. Now, but when I keep moving, that means that I need to stay at the bottom of the valley. But I go a little bit up. Okay? So I go up, down, up, down. So on the average, I don't stay in the bottom, which is the minimum. On the average, I keep on fluctuating here. So on the mean, I don't stay here. On the mean, I stay in another point. Okay? Now, when I say that, what is the axis here? the axis here is J. The axis here is a mean square error. So that means that rather than staying at the bottom of the valley, I have an additional mean square error due to the fact that I'm trembling. This is called excess mean square error. So the excess, the excess mean square error is the mean square error which goes on the top of the mean square error, which is the meaning of the mean. Now, if I stay there, I only get the noise which is circulating into the algorithm. But you know, due to that, I also get some mismatch. So my filter is not perfectly matched. No, because of that, I can analytically consider. So, you know, that means that, I mean, even if the minimum is here, you see it's J, even if the minimum is here, because I'm fluctuating, I don't stay here. On the mean, I stay there, I stay here. So because of this fluctuation, my mean square error is not the J mean, it's J mean plus something. This plus something is called excess mean square error. So the excess mean square error, which is this one, this excess mean square error is caused by the fluctuation of the coefficient the at convergence. Because I keep fluctuating. Now, if I want to remove this fluctuation, what I do? I take a mu and I remove and I reduce. I slow down. So I change mu and I make a smaller step. So then, you know, I don't move anymore. What is the counter effect of making mu small? You know, the counter effect is that I'm making all this mess to have a filter that is adapting to a non-stationary condition. So the time for convergence is not the time for convergence to reach the minimum. It's time for convergence to adapt to a changing situation. Now I'm slowly introducing you the non-stationarity. The non-stationarity is something that is non-stationary, right? But you know, I mean, you can imagine that my non-stationarity is divided into pieces of stationarity. So when I change from one non-stationarity to another, it takes some time. So the time for convergence is the number of iterations that I take to move from one optimal solution for a locally stationary condition to another optimal solution for another stationary condition. So for many reasons, I want to have the time for convergence as small as possible in order to adapt myself to a different condition, so to a non-stationary condition. Now, so computing, so you know, I mean, even the excess mean square error is a little bit tricky to compute. So you know, I gave you the intuitive way to compute how the excess mean square error is. What does it mean? Okay. So analytically, I skip it. So not requested. So I skip it analytically, but you know, it can be computed. So let's see. But what I get is the following here. Well, this is what I want. So what I get is that the mean square error asymptotically is the minimum plus something. And this plus something, which is the excess mean square error, depends on, you see, mu, the noise level, and the eigenvalues. You know, and if I want to reduce this excess mean square error, what I can do is I take a mu small, and then you know I reduce the excess mean square error. But if mu is too small, I cannot adapt to a changing condition. Which means, imagine that you have your active noise cancelling headset. You spend a lot of money with that. Huh? So you have your active noise cancelling, and then this means that if you move in one position, then you have perfect music because you cancel all the noise. but you cannot move. Because if you move a little bit, then you know the system doesn't adapt. Okay? So I mean I leave you the trouble to understand how to choose mu. Because I tell you the bound, I tell you what is the maximum level of mu that you could have, what is the maximum level you can use. My recommendation is use the mean square error. You know, don't much use the largest one, but use the mean square error. Okay? You can make a couple of big, large steps, perhaps the first, the second iteration, third. You can make a long step, still constrained to the lambda max. The problem with lambda max is that you don't have the lambda max because you need to compute the lambda of the covariance matrix of the input. Okay, and if it is non-stationary, then you know it takes too much time to compute the lambda. So it's more safer to use the mean square error. Start with that, but you know, tolerate these excess mean square error. Keep the coefficient fluctuate, but I mean, perhaps you make another loop, so you make another system that is detecting a non-stationarity condition. If you have a non-stationarity, you change mu, you rise up. And then, you know, you reach convergence. Then you have another non-stationary. Increase mu, reduce mu. Increase mu, reduce mu. Okay? So that's possible. There are possibilities. There is not one way. That's the reason why a lot of people are enjoying using, you know, the LMS. Because you can implement a different way. You can augment with the new control loop, which is checking if it is stationary or not. No, okay, this is the excess mean square error. This is the excess mean square error. Now, if I represent the behavior of J versus iteration, I get a so-called learning curve. Learning curve is the behavior of J. J, remember, is the mean square. Okay, is the error, is the mean square of the error. If I represent the mean square versus iteration, I get this nice behavior. Now, this behavior, you know, is characterized by a set of parameters. Now, first of all, J0. J0 is where I start from, so it depends on the initialization. Then, you know, it's decreasing. Now, it's not going to the minimum because there is the excess mean square error. Okay, so this is J mean. J mean will be the solution for stationary condition, which means you make a mu going to 0. But in order to keep, you know, the algorithm or the method or the filtering active, ready to react to a non-stationarity, you need to pay with this excess mean square error on the asymptotic condition. Now, what is the time for convergence that I can read in the learning curve? Now, the time for convergence approximately depends on the ratio between, you know, it's mu 1 over mu to lambda average, where a lambda average is the average of all the lambda. So this is approximately, this is the behavior, okay, of the learning curve. So analytically, you can represent by this relationship, okay, where lambda average is, or the time average is that. Now, you know, once I have this formula, I can make what he wants to do. Now, you know, I know that from this formula, I know that if I make my algorithm fast, so if I make my algorithm fast, I have an excess mean square error which is higher. If I make my algorithm slow, I have an excess error that is smaller. So, this is mu big. This is mu small. So if I make a mu big, you know, I'm fast, but at the end, you know, I have an excess error, very big. If I make a mu small, it's slower to converge, but then at the same time, you know, I have a smaller excess mean square error. Now, you know, a very intuitive way, as you was suggesting, I say, I start, and then I'm finished. I start fast, but then, you know, when I'm here, I change a mu, and I make a mu, you know, smaller. And I'm making mu smaller. And I'm making mu smaller. Okay? Now, you know, this is by scaling mu to iteration. Now, this is called gear shifting. You know when you're going with a car, okay, you are approaching, you start with the car, then you reduce, you go from, I don't know, from 6th, 5th, 4th, 3rd, to 2nd, and 1st, you see? Okay, this is scaling down the gear. It's called gear, this guy. Huh? So this method is called gear shifting. It is feasible. It is possible. And by the way, if you want to learn how to make it, you can make the optimization of the step size. That's for you. Okay? What you said is perfectly natural. You can make the optimization of the step size. And it comes out that the optimum gear shifting, you see from here, the optimum gear shifting is by shifting down fractionally on the percentage of the number of steps, which means I change delta mu with respect to the mu of my iteration, okay, depending on delta n with respect to life. Okay, so which means at the beginning I scale much, then I scale lower, lower, lower. This is what that formula is saying. Now, read that, you know, it's not goes, it doesn't go into the written, into any written exam. So, you know, but perhaps when you are using it, you need it. Okay? Since the homework number 2 is making reference to this one, so I don't care if you don't, you know, if you don't study for the written exam, but you need to study for the homework, because if you don't study for the homework, you don't solve the homework number 2. Tomorrow we finish with the recursive whisper, RLS, and I show you how to write these examples. So my goal is to comment on these examples, how to make that. I show you that this is the kernel. Here, this is the update, you know, very big, huh? complex code, right? Okay, so this is all blah 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 blah, but you know, this is the update. A equal A plus mu epsilon, and this is S. And I divide by trace of R, which is a normalization. So you know, the code is always one line. I told you, we don't write a complex code. It's one line, 10 lines, 50 lines of code. Complicated to write it, you know. See you tomorrow.